Today we're going to be talking about oscillations. So this is going to be very similar to like what we've been seeing with the spring systems that you saw from activity 5 and activity number 11. And what we're going to identify today is something known as simple harmonic motion, or SHM for short, which is just essentially like a wave-like motion that you're going to observe with things like, say, springs and systems like that. And we're going to be revisiting the mass spring system because this system is a good representative of these waves that we're going to be analyzing throughout the rest of the semester. But also on top of that, we are going to analyze two new SHM examples, which are going to be the uniform circular motion. We're going to be looking and seeing how X and Y coordinates in UCM can actually be described using simple harmonic motion. And also the same thing with the pendulum. We're going to be looking at the forces of a pendulum and seeing where SHM comes into play with the pendulum. And then we're going to be able to model an equation that represents the wave for each of these SHM systems. But on top of that, right, we're also going to need to take into account where the wave starts. Is it going to start at its maximum displacement? Is it going to start at its minimum displacement? Is it going to start at, well, at its equilibrium position? That will be addressed by means of using phase constants. Now let's take a look at mechanical oscillations through the lens of a mass that's on a spring, kind of something like this right here. And what we can see here is that we have our equilibrium position at x is equal to 0, so it goes throughout this dotted line right here. And we're going to assume that going to the right, that this is how time advances, as you can see up here. And we saw earlier in the semester that we know that the restoring force is described by Hooke's law, where we have F is equal to negative kx, and k is going to be our spring constant, x is our displacement, and F is the force that's experienced. And I'll review this a little bit later as well. And if you look here, if you look at how the system's moving, you'll see that this mass spring system is at its equilibrium position right here in the blue, but then it goes over to here, which is going to be, well, pulled all the way down. So it's going to be its max expansion, and then we go here, it's equilibrium position again, and then we go here, this is going to be our max compression, and then we go here, this is going to be our max, well, it's going to be our equilibrium right here. So with this, you'll see that you get a wave shape that goes something like this. You can kind of like trace a wave kind of like this through your system like this. And that will describe the motion. I'll do it one more time just so you can see. So it goes something like that. Now let's take a look what simple harmonic motion is, or SHM for short. So if we take a look at our displacement graph that we saw for our mass spring system on the previous slide, what we'll see here is that we get a wave that looks kind of like this. You'll have a maximum displacement right here of positive xm at the top here at t is equal to 0 possibly, and then you'll eventually reach your equilibrium position, and then you'll reach this point here. So then you have another maximum displacement as well, and then you'll go here to equilibrium position again, and then you go here to another max displacement. So that is going to be one cycle, and you can see that this cycle is going to be modeled by means of using t here. T is going to be the period. And the way we actually model this displacement is we say that xt, x is a function of time, is going to be equal to xm, where xm is going to be the amplitude of our wave here, and we multiply by cosine in this case. You could use cosine or sine, but in this case cosine is better because, well, you can see that the maximum is at 0, t is equal to 0, that is. And then, yeah, that will give you your wave. And then you have this thing called a phase constant right here, which is going to be important to keep in mind. And then, again, you could use sine as well. So we got the red, that's going to be our amplitude. We got this omega here, that's our angular frequency. And then we have these in green, which is going to be our phase constant. And this angular frequency can be determined by means of using this here, where angular frequency is going to be the square root of k over m. And again, we discussed about that earlier, but I'm going to review it in the next slide. So angular frequency. And you have this here, where this is going to be a whole bunch of different parameters here, where I'm going to describe each of these. So you got f, this is going to represent the frequency. So what does the frequency represent? Is essentially 1 over the period. So the frequency essentially represents how many cycles there are per unit time. And this can be obtained from the angular frequency by means of doing omega over 2 pi. And also, if you stick an omega as square root of k over m, you can see that's what you get for a spring mass system. So that's frequency. An important note, period is the inverse of frequency. And then, if you recall, right, if you know the displacement graph, right, you can figure out the velocity and the acceleration graphs by means of doing differentiation. You'll know that if you take a cosine curve here, right, you'll get a sine curve like this. And then if you differentiate once again, you'll get another cosine-like curve as well. And then you model your position, your velocity, and acceleration, with your position being the same as, well, this equation that's right over here. And then you get your velocity, vt, by means of differentiating your position with respect to time, and you get negative omega xm times the sine of your function. And that will give you this curve right over here. And then you get your acceleration, that's going to be differentiating v with respect to t. And then you get negative omega squared xm cosine. And if you look here, this acceleration graph is essentially just going to be flipped over compared to the displacement graph. And also notice that each of these graphs have the same period, t, same period here, and same period here. And then if you take a look at the amplitudes, like for instance, you take a look at acceleration, you'll see that the amplitude is going to be omega squared x, while for velocity it's going to be omega x, and for displacement it's going to be x. So you can determine that based on whatever this factor is going to be on the outside of your cosine or sine function. So x, you have xm, omega xm here, and omega squared xm here. Look at two more cases of simple harmonic motion in addition to our mass spring system, that is. So what I'm going to be doing is I'm going to be showing the three systems that we're interested in here for SHM. And we're first going to be looking at the spring, and then we're going to look at the pendulum, and then we're going to look at uniform circular motion for a little bit. So we know a mass spring system looks kind of like this, and we know it's going to, we can have it expand like that. We can have it contract like that. But what about a pendulum? Oh, and also, by the way, if you want to refer to the spring systems lecture, that would be great for you to review the spring motion. But anyway, most of this is covered in the review, by the way. And then, if we take a look at the pendulum, we have like a ceiling here, and then we have a pendulum like this here, so connected by a string, and then we happen to have this, we call it a bob, and then if we see the motion, right, it's going to kind of swing kind of like this. Go for its equilibrium position there, and then come here, and then it's going to come back like that. And then, if we want to model the system, it might be great for us to actually put these dotted lines right here. And we'll eventually see that there's going to be an angle that's going to be formed between this vertical and then this, well, string. But we'll get to that when we get to it. But before we do that, let's take an interesting look at uniform circular motion. So uniform circular motion, we know that we have an object that's going around in a circle kind of like this. We know the velocity is going to be tangential to the circle, so you can clearly see that. And then let's suppose this time I'm going to set up an XY coordinate system like that. Let's see what we can do about this and how we can maybe track the position of these particles. So what I'm going to do is I'm going to set up a vector here, and I'm going to set up an angle that is formed between the horizontal and then also the vector here. And I'm going to say that this dotted distance is going to be xt, and this dotted distance is going to be yt for this point right here. If suppose that the particle is right here. What we can do is we can say xt is going to be equal to xm's cosine, and then yt is equal to ym sine. And essentially what this turns out to be is just more or less a parameterization of our circle here, where essentially we are just writing our x and y coordinates as a function of time. Now let's take a look at the pendulum system now. And I'm going to assume that the bob of the pendulum and the string is going to be on the right side of this vertical dotted line here. And I'm going to be setting up the forces that are going to be on this pendulum, where we have, well, first, before we do the forces, we have theta being the angle that is going to be formed between the vertical and also the string. And now let's put our forces on. So we got mg, which is downward, and we have a tension which goes this way. And for the sake of this sort of problem, we're going to be assuming that theta is going to be extremely small. So we call that small angle approximation. And for the sake of this problem, we're going to be assuming that the acceleration in the x direction is going to be much greater than the acceleration in the y direction. And if we do that, we will see that t cosine theta, that is the vertical component of our tension, minus mg, our weight, is equal to 0. And we're essentially more or less assuming that the y directional acceleration is negligible for this sort of problem. And if you solve this, you'll find that t cosine of theta is equal to mg. So that's what we get from our y equation. And then it's time to move on to the x. The x equation, the only force that is going to be acting in the x direction at this point is going to be the horizontal component of the tension, which is going to be negative t sine theta. And that is going to be equal to m times a, whatever that acceleration is in the x direction. In this case, that acceleration in the x direction is going to be the second derivative of our position with respect to time. Now let's take a look and see if we're able to derive the angular frequency for these small pendulum oscillations. So what we have here is our pendulum bob and its string and the vertical, well, line here. And we know that this pendulum has a length of L, going from this point here to, well, the bob itself. And then we happen to have a distance of x here going from the vertical line to this point here. And then we happen to have an angle of theta that's formed, just like we saw in the previous slide. And thus you get a right triangle. And I'm just going to take the results that we had from the previous slide. The ones that are in the black box are the most important, because that's going to be used to derive what's going on here. So let's take a look at our trigonometry, we have sine of theta is equal to x over L. So we take x over L. That makes sense for a right triangle. And yeah, simply applying trigonometry. And then the next part here, what we have here is we're going to be taking this equation right over here and then going whoosh right over here. We get negative at t times the sine of theta. What is sine of theta equal to? X over L. We stick in x over L for sine theta, and thus we get this on our left-hand side, and then we set this equal to m times our acceleration, essentially. And then with this, we can isolate the second derivative here, where essentially I'm just dividing both sides of this equation right over here by m, and what I get is simply this here. And then, now I'm ready to be able to apply the small angle approximation to the tension and also the cosine function. So what does that mean? Now we're going to be focusing on this one here. So this is black box equation. And we know t cosine is equal to mg. But since we're dealing with very small angles, it is okay for us to assume that cosine theta is approximately 1. And if we do so, we can say that tension is, well, equal to mg in this case. And then, using our tension is equal to mg, we can stick it right back up into this equation here. And then we get our second derivative of x with respect to time is equal to negative our tension. Remember, tension's mg divided by ml times x. And then that approximately turns out to be negative g over L times x. Why? Because the masses cancel. And then what you find is that you get an equation that is going to be very similar to what we saw before with the mass spring system. You get a second derivative of x with respect to time here, just like the mass spring system. And then you happen to have some angular frequency squared here. So in this case, it's going to be g over L, while for the mass spring system, it was different, times x. And that's all equal to 0. And thus, you get your angular frequency is equal to the square root of g over L. And you could use pretty much more or less kind of the same strategy to solving this differential equation here that we did for the mass spring system to get the angular frequency for the mass spring system. And thus, that is going to be your angular frequency for your pendulum. And if you want to give it a shot, maybe check it whether or not this works. I mean, feel free to use the methods that we're seeing in the mass spring system derivation. And yeah, just to kind of sum it up, this ordinary differential equation is exactly the same as our mass spring system. Now let's take a look at how we can measure this phase angle. And if you recall, the phase angle is going to be this symbol right here, which is going to be phi, which essentially allows us to either push a sine or cosine function to the right or to the left. So let's see how we can fare with this. What we have here is we want to fit this curve here that looks kind of like a sine function here, kind of like a flipped over sine function, except we want to fit this to the model of a cosine function. So let's see how we can actually figure out a phase angle that actually gives us exactly this. So we know if t is equal to 0, then we know that this equation right here, xm times cosine, must turn out to be, well, just cosine of phi. So that's what you get here. So x times cosine of phi. And we know at t is equal to 0 right here, we know that, well, x is going to be equal to 0. So that means that we have cosine of phi is equal to 0, which gives us one of two different solutions. We have phi is equal to pi over 2 or 3 pi over 2. And our goal here is to figure out which of these is correct. So what we can do is we can maybe just kind of pick one singular point on this curve here, and then we ask ourselves, this point here is going to be equal to a quarter of the period, so that's t is equal to the quarter of the period. And we can evaluate omega t, and that's going to be equal to 2 pi over, well, your period, times your period over 4. That turns out to be pi over 2. That's for sure. Omega t is going to be pi over 2. And thus, what we can find here, right, is that we end up with this here when we have omega t is equal to pi over 2. Because if you think about this, right, what you have here is if you take cosine of pi over 2, then, oh god, what the hell? Now let's take a look at the math behind this. So what we have here is if we have this point right over here, we know that's going to be a quarter of the period, so that's why we call it capital T over 4. And if we want to solve for omega t, we know omega is going to be 2 pi over t, and we multiply it by our period over 4, and that definitely gives us pi over 2. And also, if you keep in mind that this point right here at a quarter of the period is going to be negative xm. So that's what x is going to be equal to. You then take your omega t, stick it right back into this equation here, and then you get x is equal to xm times cosine of this, well, pi over 2 plus phi. And you know this is all going to be equal to negative xm. You divide both sides by xm, and then you get cosine of pi over 2 plus phi is equal to negative 1. And with this in mind, you know that cosine of, well, just something inside of here is equal to negative 1 will give you that inside factor, this pi over 2 plus phi, to equal pi if you do the arc cosine. So you'll find that pi over 2 plus phi is equal to pi. And then, once you solve this out, you know that phi has to equal pi over 2. And that is going to be your phase angle for this particular wave here, and how to appropriately model it for this cosine function. Let's finish off by taking a look at the problem of the day, where what we have here is that we have a wooden block that's going to be attached to an ideal spring, very similar to like what you're going to be talking about with your activity today. But the thing that's a little bit different here is that the spring is going to be situated horizontally on a frictionless table. So that way we don't really have to think too much about gravity. Just to kind of simplify the problem a little bit. And it's going to execute simple harmonic motion. And then what we see here is that we know that the spring has a force constant of 20 newtons per meter. And we know it takes 0.25 seconds, a quarter of a second, for the block to go from its maximum extension, keep that in mind, maximum extension, to the equilibrium position of the spring. And if we think about that, there's going to be a special fraction of a period that's going to be able to describe this, well, block going from its maximum extension to its equilibrium position. And our goal here is to figure out the mass of the block. So what we're going to need to do here is something that's a little bit interesting. What we're going to need to do here is combine both the aspects of having our angular frequency equaling 2 pi over a period. That's one way we can describe the angular frequency, but also take advantage of our square root definition, where we have the square root of k over m. And if you were to equate these two together, you can actually solve for m from this. You get mass is going to be equal to this here. And with this, you're now ready to solve. So we know that this oscillation takes a quarter of a second to go from maximum extension to the equilibrium position. And what I was mentioning about a little bit earlier is if you think about it, you're going to, I'll be going over a quarter of the period over that 0.25 seconds. So if you're going over a quarter of the period, then that means that the whole period is going to be 1 second. And then from there, it's just pretty much plug and chug. You got your mass, stick in your force constant, your spring constant, your time here, and then you divide by 4 pi squared. You get 0.51 kilograms. And I'm just going to highlight this over here because this might be very important for the exam. Now let's move on to talking about the kinetic and potential energy for this mass spring system, and we'll eventually see that these energies can be described in the context of waves. So let's take a look and see if we're able to get a wave solution for this system. If we consider the net force, which of course by Newton's second law is going to be mass times acceleration, we know that we can write that as mass times the second derivative of y with respect to time. And from our information from the previous slide and our derivation, we can see that the net force will be negative ky for this mass spring system. And a good guess for the solution to this particular equation right here, this is known as the differential equation, by the way, is this, where you have y is equal to a times the cosine of omega t, with omega being equal to the square root of k over m. And cosine or sine works for this sort of differential equation, but we're going to be sticking to cosine for now. And to confirm that this sinusoidal function works, this cosine function works, we're going to check the solution. So we evaluate m times the second derivative of y with respect to time. We get mass times the second derivative of y, which we know is going to be negative omega squared times a times the cosine of omega t. And then if you use omega, which is equal to the square root of k over m, we know omega squared is going to, of course, become k over m here. And that's a simple substitution. And then you end up getting negative ka cosine omega t. And if you take a look at this, you can see that negative k can be factored out, and then you can put a cosine omega t in parentheses. And what does a cosine omega t look like? It looks like y. And if you look at this, you'll see that m times the second derivative of y with respect to time will eventually turn out to be equal to negative ky, which is exactly the same thing as this equation up here. So these solutions right here in red work out. So put a check mark there. Now let's start getting into the energies for the spring system. And let's start by talking about the spring kinetic energy. So we know kinetic energy is 1/2 mv squared. And then we stick in our speed. If you differentiate once, you take dy dt, you'll get negative a omega sine omega t. So that's just kinematics there. And that is going to be your v inside here, and then you're going to square that, and then multiply by 1/2 m. You'll get 1/2 m a squared times omega squared, which again we established is k over m. And then we multiply by sine squared omega t. And if you were to condense this down by means of, say, canceling the m's, like that, you'll end up finding that your kinetic energy is equal to 1/2 k a squared times the sine squared of omega t. Now, let's take a look at the spring potential energy. You got U is equal to 1/2 ky squared, and that is equal to 1/2 k a cosine omega t squared, and that is equal to half ka squared times cosine squared omega t. So we got our kinetic energy right here, and we have our potential energy right here. And our goal is now to see what the total energy is going to be. And recall, that is the sum of the kinetic plus the potential. As you can see here, total mechanical energy. And if we add this up, we see that we get this here, where we get the same amplitudes. We get 1/2 Ka squared here and here. So this matches up with this. And you might notice that if you did some factoring, you'll notice that you can get sine squared plus cosine squared, which we know is equal to 1. So our total energy will turn out to be 1/2 Ka squared, where we know that K, being the spring constant, is going to be, well, constant. And we know A, being the amplitude of our oscillation, is also going to be constant. So if those two, K and A, are constant, then that means our total mechanical energy will also be constant. So we have conservation energy in this case. And if you were to take a look at what these solutions look like for the displacement, for the velocity, and for the acceleration, you'll notice that you get a waveform here, like this, for y. And you see that the amplitude of our wave is going to be a. And you see that the period of our wave is going to be capital T. And then if you take a look at velocity, you'll see that your new amplitude becomes a omega. So the amplitude changes. And you also see that the wave changes a bit as well. It is phase shifted. And then you have the acceleration, which is going to be a omega squared as the amplitude. And then you can see that you get this shape here, which is, again, another phase shift from the velocity curve. And we'll get into the more precise details regarding these waves later in the semester.